Today's lecture is about the growth of functions and asymptotic notations. So what is exactly the meaning of a growth of functions? The growth of a function is the behavior of this function as its input gets large. So in other words, if its input goes to infinity, how the function will behave. And the asymptotic notation is a method that is used to describe this growth mathematically. To explain the meaning of a growth of functions, we will present an example that compares the running time of two algorithms. Suppose an algorithm does this amount of multiplications and another algorithm does this amount of multiplications. Which algorithm will be faster? Before we answer this question, we would like to explain briefly how did we get these functions. In the analysis of algorithms, when an algorithm is analyzed, the result of this analysis is a function in terms of n, where n is an input to this algorithm. For example, if the algorithm is processing an array, then n is the size of this array. And if the algorithm is processing a piece of code that consists of a loop, then n will be the number of iterations in this loop. In general, the function obtained from the analysis of an algorithm represents the number of steps or number of operations executed by this algorithm. Later, to know the running time, for example in seconds, all what you have to do, divide the number of operations executed by this algorithm over the number of operations this computer can execute per second. So let us find out which algorithm does more multiplications than the other by finding some values of these functions for a sample of n. To compare the growth of these two functions, we have created a table for a sample of n. So we would like to know, as if these two functions go on race, which function beats the other function for each value of n. Observe that when n is equal to 10, there is a tie, so there is no winner. But also observe that any value of n before 10, the first function gives values that are higher than the other function. That means that the winner is the cubic function. And also after n is equal to 10, notice that the first function gives values smaller than the other function. And in this case, the first function is the winner. And if you try to continue for n that goes to infinity, you will notice that is always the first function is the winner. Mathematically, how do we write this? We write it as follows. We say that 5n squared is always the winner, which is less than or equal to half n raised to power 3. But when this happens, it happens when n is greater than 10. So the conclusion is, for small values of n, which is less than 10, the first does fewer multiplications, which is this one. And for larger values of n, which is after 10, the second does fewer multiplications, which is the second one. In this case, which one to pick as the correct answer? The one that we need to pick for the correct answer should be this one. Why? Because if these are the running time of algorithms, we are not interested to test our algorithm for small input. We would like to test our algorithm for large input and observe how the algorithm behaves. We can also find the relationship between these two functions by drawing their graphs. This is the graph of the two functions. The x-axis represents n, and the y-axis represents the value when n is substituted into these functions. The graph, the red color graph, is for the second function, and the blue color graph is for the first function. Notice that for n less than k, the red color graph is on top of the blue color graph. So that means the running time for the blue color is smaller than the running time of the red color. If these two functions go on race, so the winner will be the blue color because it spends time less than the other one. but after n is equal to k, then the behavior of the two functions will change. So notice that the blue color graph is on top now of the red color graph. So which one is the winner now? The winner is this function. Why? Because it does fewer number of multiplications than the other one. So we say that the second function always less than or equal to the second function whenever n is greater than 10. So in terms of growth of functions, we say that this function grows no faster than the other functions. In other words, when n goes to infinity, it is always that 5n square is in lower level than the other function, which is half n raised to power 3. Our next question is how these constants can affect this relationship. In other words, can we change the constants, for example, 5 and half of these two functions, and make this function smaller than the other one? Let us find out by an example. Now what we will do, I will replace 5 by a large value, and also I will replace half by a very, very small value. And then let us see if this function can become smaller than this function when n goes to infinity. Here is our new table now. So this is the first function. Instead of 5, it is now multiplied by 10,000s. And this is the second function. Instead of multiplied by half, now it is multiplied by 10 raised to power minus 5, which is very small value. By again substituting for some values of n, and as if these two functions are on race, we would like to know which function beats the other one. First, where is the tithe? The tithe is when n is equal to 10 raised to power 9. And any value before n is equal to 10 raised to power 9, notice that the first function gives values larger than the second function. So which one is the winner? The winner is the second function. But after the value of n is equal to 10 raised to power 9, then notice that the first function gives a smaller value than the other function. So the winner is the first function. And if you try to continue this table for large values of n, again you will notice that this function will be always less than or equal to this function, and we write it mathematically 10,000 n square less than or equal to 0.0001 n raised to power 3. But when this happens, it happens when n is greater than 10 raised to power 9. So the difference between this relationship and the previous relationship is that this relationship holds when n is greater than 10. But this relationship holds when n is greater than or equal to 10. But that will not change the relationship. Is that if you multiply any constant by n square and any constant by n raised to power 3, still this relationship will stay, and this function will grow no faster than this function. In our conclusion, changing the constants in these functions will not change the growth relationship. Since changing the constants that are multiplied by these two functions will not change the growth relationship, in other words, any values you multiply n raised to power 3 as a constant, and any constant you multiply n square, it is always that this function grows no faster than this function. Also, since we are interested for large values of n, then we need a way to compare two algorithms by ignoring the constants, at the same time by considering only large values and ignoring small values. In this example, we would like to explore the running times of some functions that appear quite often in algorithms. These functions, here we have linear, here we have log base 2n, here we have n multiplied by log, here we have n square, quadratic, and here we have exponential. Suppose now you have a computer that executes this number of steps per second, 1 billion. And suppose that the algorithm executes f of n steps. Then to compute the time in seconds, you divide number of steps over a million, you will get the answer in seconds. So for example, if you have n is equal to 100, then number of steps will be 100 for the linear. I'm talking about this linear function. And when you divide it by 10 raised to power 9, then you will get the answer 10 raised to power minus 7. And this is equal to 10 raised to power minus 1 multiplied by 10 raised to power minus 6. And here you have minus 6 is equal to microsecond. So simply we write that this is equal to 10 raised to power minus 1 microsecond, which is equal to 0.1 microsecond. By following the same calculations for the other functions, the result of these calculations are listed in this table. So to compare the running time of these algorithms and determine which one is faster than the other ones in order, we need to go over a sample of n and compare the running time of these functions. As an example, for n is equal to 40, the linear function spends 0.04 microsecond. The log2n spends 0.005 microseconds, so it is faster than the linear. And for n multiplied by log n, it spends 0.213 microseconds. And for the quadratic, it executes in 1.6 microseconds. And for the exponential, it is 18.3 minutes. So all of the running times of these functions in microseconds, except the last one, see, it is in minutes. So there is a very big difference between the running time of all functions compared to the exponential. Now let us increase the input by 10 only, and let's go for 50, and let us see how the running time of the algorithm will change. Now the running time of the first algorithm, linear, does not change quite much. Even it's not noticeable, 0.04 to 0.05. The second algorithm is the same. For the third one is the same, and also for the fourth one is the same. But for the exponential, see, notice that if you just increase the input from 40 to 50 just by 10, and see how the running time jumps. It jumps from 18.3 minutes to 13 days, just only for 10 difference between the input and the previous input. Now let's go for 100. And for 100, see, all of these algorithms gives the running time in microseconds, even less than 1, except maybe the quadratic equation, 10 microseconds. These are less than 1. But notice that for the exponential function, the running time is 4 times 10 raised to power 13 years. In practical, we can say that the program will never terminate because no one can live this number of years. Now we can say that which algorithm grows faster than the other one. When we arrange them, then we will see that this function will be in the lowest level, then comes n, then comes n log 2n, n square, and finally on top will be 2 to the power n. So when I want to see the relationship between these two, we can say that log 2n grows no faster than ny because log 2n will be in lower level than n. Also, if I want to compare, for example, this function with this function, so we say that n log 2n grows no faster than n square. Why? Because n log n will be drawn in lower level than n square. Next, we want to use a mathematical notation that describes the growth relationship between any two functions. This notation is called order of a function. So what does it mean, order of n? What does it mean, order of log 2n? So we will use these functions as an example to explain the meaning of order of a function.